All right. Hello, everybody. Welcome to another physics video lecture. Today we are going to start talking about collisions, specifically elastic collisions. Okay? So we'll get to what the elastic part means, but what we're talking about today is what happens when two things smash into each other, right? Now, in order to understand what happens when two things smash into each other, we need to understand their momentum. Okay, so we need to go back and just do a real quick, brief review about momentum. Now remember, momentum is a mass in motion. In order for something to smash into something else, at least one of those two objects has to be moving. Luckily for us, our equation for momentum is super simple, okay? In order to find momentum, all you have to do is take the mass of the object and multiply it by its velocity. How big is the thing times how fast it's going? That's it, okay? So we're gonna take this one simple equation and we're gonna use it in a pretty interesting way, okay? Now, I'm gonna let you guys know right now that the equation that we're gonna get to, it's gonna look complicated, but I promise, stick with me. We're gonna break it down and it's actually a lot easier than it looks, all right? Okay, so the next thing we have to talk about is the law of conservation of momentum. So what we're gonna see a lot of for the rest of the year is that things are conserved in physics, okay? And one of the things that is always conserved is momentum. Now, what does it mean to be conserved? If you conserve something, you save it, you protect it, nothing happens to it. So what that means is even though two things smash together, all right, the momentum that you have before those two things smash together is always going to be equal to the momentum after those two things smash together, okay? And this is really at the heart of everything that we're going to talk about when we talk about collisions, okay? The fact that momentum is conserved allows us to calculate so many different things, all right? So let's look at a table and let's break this down. So what is an elastic collision? Well, when you think of something that's elastic, right, what do you normally think of? I'll pause. Something that is elastic is usually something that stretches, right? Okay, it's good. I want you to keep that in your mind. Because whenever you think of an elastic collision, whenever you heard the word elastic, I want you to think of rubber, specifically rubber balls. And what do rubber balls do? Well, rubber balls bounce. And that's what an elastic collision is. An elastic collision is when two things are moving, they hit each other, and they bounce off. Okay? So again, two things are moving, they hit each other, and they bounce off of each other. All right? So there are a few examples of this. We'll talk about a couple in a second. But what we're always going to see here, and what's always super important, is understanding the momentum before a collision and the momentum after a collision. Okay? So in order to find the total momentum, okay, and I actually think that I have this in a different slide. We'll get to it. Okay, so we have the total momentum here. So to find the momentum, to find the total momentum, all you do is you add up the momentums of the two objects. Well, that's pretty easy. Okay, so we're going to start off with this, all right? Notice we have a mass times a velocity plus a mass times a velocity, okay? To find the total momentum, just add the momentums of the two objects. Easy enough. So we'll just say we have two random objects that smash into each other. Let's say that there are these two markers. These two markers are both moving, and before they hit each other, the momentum before they hit each other, you take the mass of the first marker, multiply it by its velocity, and then you add that to the mass of the second marker, multiplied by its velocity. So this is before they hit each other. Now, we have the momentum after, and we do the exact same thing, right? The markers are moving, they hit each other, and they bounce. Well, now, each object is going to have a change, right? Their masses are going to stay the same. So the mass of the first object, the purple marker, is the same. Okay? But it's going to have a new velocity, and we call that v1f. That's its final velocity. Same with the mass of the second marker. Okay? The black marker is going to have the same mass, m2, but it's going to have a new velocity. We call that v2f. So when two things bounce off each other, usually, for the sake of this class, we think that their masses stay the same. So that's why we have an M1, an M2, an M1, and an M2, right? But their velocities are what are changing. They're moving, they hit, and then their velocity changes. So we have a V1I, that's the initial velocity of the first object, a V2I, the initial velocity of the second object, a V1F, the final velocity of the first object, and a V2F, a final velocity of the second object. Now again, I know this looks complicated. Don't worry, there's a slide I'm about to show you where I list all of those. Okay, you're gonna be fine, okay? So now a big thing to remember, and what you're gonna see, is you have to remember that the momentum before the collision always equals the momentum after the collision, which means that these two always equal each other. So this is our total equation for the day, which looks like a lot, but it's actually easy to unpack. And this whole thing, just like this, is on your equation sheet. So you do not need to memorize it. You have this, okay? Just like this. I wrote it just like this, okay? All right, so the next thing we need to look at is what is conserved here? Well, we already saw in the last slide, right, that momentum is always conserved, always. So whenever you see that, just be like, well, momentum is always conserved. But elastic collisions are special because an elastic collision, kinetic energy is also conserved. So remember, kinetic energy is the energy of movement. So if you think about this, the two objects were moving when they started, they bounce, and they're moving when they finish. Even if one is not moving, okay, like for example, you're gonna see this twice today. The big example with elastic collisions are pool balls, right? You play pool, you got one ball that's moving, it hits another ball, the first ball stops, and the second ball keeps moving. Okay, you're taking movement, turning it into movement. That's why kinetic energy is conserved. You're taking energy that is of movement and turning it into energy of movement. Okay? An example, like I just said, pool balls, they bounce off of each other. Another great example are these Newton balls right here. I'm sure you've seen this on somebody's desk before, maybe you have one in your house. But look, the balls hit each other and movement turns into movement. They bounce off of each other and the momentum before equals the momentum after. Okay? I tried to make these notes as condensed. This is really everything you need to know about elastic collisions. So take a second, pause, write this down, make a nice little chart. Okay? If you write all this down, it's going to be super helpful later. So pause. You good? Okay. So a couple things. I wrote this, and I know that this is a lot, okay? But this is just another way of spelling all this out because I wanted you to have it in two different ways. Okay, two objects bounce off of each other, so they're separate before the collision and they're separate after the collision. They start off separate, they hit each other, they bounce, and they end up separate. Okay? So the objects start off separate, which means that each object is its own object. So you have M1V1 plus M2V2. And they end separate, right? They bounce off each other. M1V1, M2V2. The only thing that's changing are the velocities. Okay? The starting velocity of the first object, the starting velocity of the second object, the final velocity of the first object, the final velocity of the second object. Notice the momentum before the collision always equals the momentum after. Again, I just put that in there, showing it to you like this because I understand that students will look at this and think it's super complicated, so I just want you to see it a bunch of different ways. And I was thinking that maybe if I just write it a couple different ways, it would be helpful. So, fingers crossed. But this is your whole equation. This is what we're working with today, and we're just going to do it, all right? If you forget what any of these are, I give you a whole list, okay? So again, M1 is the mass of the first object. M2 is the mass of the second object. That's easy, right? Purple marker, black marker. They both have a mass. When we're starting, the purple marker has a velocity. We call that V1I. It's the velocity of the first object, and it's its initial velocity, how fast it starts. Same with V2I, right? The mass of the second object, that's our black marker. The black marker has a velocity. We call that V2 because it's the second object, and I because it's the initial velocity. After they hit each other, we now have a V1F. That's the velocity of the first object, or the final velocity of the first object. So after they bounce, how fast is it going? and a v2f, which is the final velocity of the second object. All right? Okay, so we're gonna do 3 examples here, and this will make more sense as we go through it. So if you have ever needed to work with me and write this down, today is the day. Working through these problems with me is super, super important, okay? Because it is not difficult as long as you lay everything out correctly, all right? Okay, let's do it. All right, so our first example obviously involves pool balls, okay? So like with anything else, the thing that we want to do is we want to make a list of everything that we know, all right? So this is going to take some writing, might even take some erasing, but we can do this. All right, we have a 0.5 kilogram pool ball. We're going to call that object number 1. Mass 1 is equal to 0.8 kilograms. Did I say 0.5? It's 0.8. Okay, good. And it is moving at 45 meters per second. All right, so that is its starting velocity. So we're going to call that v1I, okay? And that is going to equal to 45 meters per second. It strikes a resting pool ball with a mass of 1.2 kilograms. Excellent. So we now know the mass of the second pool ball is 1.2 kilograms, right? And we know its initial velocity. It's resting, so what's its initial velocity? The V2 initial, I like to put a little thing on these eyes to make them look different than the ones, is equal to, you guessed it, 0 meters per second, because it's resting, it's not moving. If you've ever played pool, usually one pool ball is moving and the one that you're trying to hit isn't. Now, if the first pool ball comes to rest after the collision, so that tells me my final velocity, right? My V1F is equal to 0 meters per second because the first pool ball stops moving after the collision, so its final velocity is 0. Find the final velocity of the second pool ball. So we are looking for V2F. Question. All right, so again, pretty straightforward. This is everything we know. Now, our equation here, I'm gonna write this down, okay, is the following. Maybe I'll do it from right here. Ready? It is M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Again, the momentum before, the way you find total momentum is you just add up the momentums of both objects, and the momentum before is equal to the momentum after, okay? Now, all you have to do is plug your numbers in. It actually gets pretty easy at this point. Once you get to here, this gets pretty simple. So watch. M1 is 0.8 times V1I is 45. Put parentheses around this because we got to do the multiplication before the addition. M2 is 1.2 times its initial velocity, which is 0. That's very helpful. We have mass 1 is 0.8 times mass 1 final velocity, which is also 0, also useful, plus M2, which is 1.2 times V2F, which is what we're looking for. Now, that looks like a lot. So you got to remember, you always do multiplication before you do your addition. So you got to multiply all these out first, okay? Now we have two that are super easy. 1.2 times 0 and 0.8 times 0 are awesome because anything times 0 is 0. So 1.2 times 0 is 0. 0.8 times 0 is also 0. So the only real multiplication we have to do here is 0.8 times 45. And if I have it set up, there's my calculator. So I'm sorry, this is kind of in the way, but 0.8 times 45 is going to give me my answer, which I got to move this. No, don't go away. I didn't see it. I just hit answer. There it is. That gives me 36. Okay. Can I move this on just a little bit? Why won't this move? There we go. 36. I'm going to move this a little bit back. Okay. So what I have here, 0.8 times 45 is 36. That's plus 0. So I don't care about any of this. This equals 0.8 times 0, 0. So I have 1.2 times V2F. You see how I just brought everything down? Now this looks super clean and really easy. We want to get V2F by itself. This is multiplication. This should look pretty straightforward. So we do the opposite of multiplying, which is dividing, and we want to move the 1.2. So we divide that side by 1.2. We divide that side by 1.2. We bring back our calculator, and we're going to take this 36 and divide it by 1.2, and that gives us our answer, which I'm going to go second answer to see it, which gives us a final velocity for the second object, V2F, 30 meters per second. Okay? So when the first pool ball crashes into the second pool ball, it's going 45 meters per second, but it's smaller, so the second pool ball is a little bit bigger, so it is moving away at a slower speed, right? Because it's bigger, so it's going to go slower. Momentum is always conserved. Take a second. You like that? These are fun. If you're into the puzzly aspect of this class, which is the best way to see it, these are actually a lot of fun. I like collisions a lot. All right, you good? Okay, let's do number 2. All right, number 2. Not a lot of examples in the real world I can think of, so we're going to talk about bumper cars. All right? Okay, so now we have, I'm just going to write this all down, same thing, make a chart. We have a 100 kilogram car is moving at 10 meters per second. We're going to call that mass 1. So mass 1 is equal to 100 kilograms, and it's moving at 10 meters per second, so that's our first velocity initial, V1I, 10 meters per second. It strikes a second car with a mass of 200 kilograms. We're going to call that M2, 200 kg, moving at 8 meters per second. So that is our V2I. The initial velocity of our second vehicle is 8 meters per second. Okay, if the first car is moving 5 meters per second after the crash, this is different. So now we have a V1F of 5 meters per second. Okay, so the first car is now still moving after the crash. Okay, how fast is the second car moving? So we're still looking for V2F. Okay, the only real difference here is that both objects start with a starting velocity and both objects end with a final velocity that is not 0. So that's why I wanted to show you how to do this one. Okay, second verse, same as the first. Let's do it. Okay, our equation is M1 V1I plus M2 V2I. So the initial momentums, M1 V1 final plus M2 V2 final. I know this is in the way. I wish I had a calculator that was smaller up there. I'm trying, guys. All right, plug your numbers in. Okay, M1 is 100 times its initial velocity, which is 10, plus mass 2 is 200 times its initial velocity, which is 8. That equals M1, which again is 100, times its final velocity, which is 5, plus M2, which is 200, times its final velocity, which is what we are looking for. It's a calf stretch. All right, a lot of stuff going on here. And remember, always do the parentheses first, PEMDAS. So we're going to do this multiplication first. So I'm not going to use a calculator for this. I'm just going to do this in my head. 100 times 10 is 1,000, plus 200 times 8 is 1,600, or 1,600. 100 times 5 is 500, plus 200 times V2F is 200, times V2F. Isn't that crazy? Okay, next step, keep doing basic math. So I got 1,000 plus 1,600, this gives me 2,600. And that's going to equal 500 plus 200 V2F. Now, we ultimately want V2F by itself. So we've seen equations like this before, but we haven't seen one for a minute. In order to get V2F by itself, we're eventually going to have to move the 200, but that's multiplying. If there is addition, you always got to move this number, or subtraction, you got to move this number first, all right? So we have to move this 500. How do we do that? Well, this is being added. The 500 is positive, so we have to do the opposite of adding, which is subtracting. So I'm going to subtract 500 from that side. Whatever I do to this side, I have to do to this side. 500 minus 500 is 0. And this gives me 2600 minus 500, which is 2100. And that equals 200 times V2F. And now, again, if you do this right, you're always going to get back to this point right here, okay? We want V2F by itself. So this is multiplication. We have to do the opposite of multiplying, which is dividing. 200 divided by 200 is 1. It cancels out. And I'm pretty sure I know the answer to this. I'm going to double check here. So I'm going to clear this. And 2100 divided by 500, I think is 10.5. 4.2. Oh, divided by 200. What are you doing, Mr. Norris? Just making up numbers? Just making up numbers. 2100 divided by 200 is 10.5. There we go. So our answer is, I'm right all the way down here, V2F equals 10.5 meters per second. Now this is going to be important in the future. I said assume that they are moving in the same direction. Why did I do that? Because it makes the problem easier, because if they're moving in the same direction, that means both of their velocities are going in the same direction, and that means that both of their velocities are positive, okay? We'll see more on that when things start smashing together. For the time being, we're just focusing on this, okay? If their velocities go in opposite directions, okay, then we have to see them as opposite directions, okay? But we'll get to that next class. Okay, good? Good. All right, a lot of writing. Okay, one more and then we're good. Okay, we're back to pool balls because I couldn't think of another example, but this one is going to be different than the first one. So watch how this is different. All right, we're starting off. Mass 1 is 0.8 again. It strikes a resting pool ball. So that means with a mass of 1.2. So mass 2 is still 1.2 kilograms. The velocity of the second pool ball is resting, so that means V2 initial is equal to 0 still. So starting off pretty similar. If the first pool ball is moving 20 meters per second after the collision, so that means my V1 final is 20, and the second pool ball is moving 30 meters per second, that means my V2 final is 30 meters per second. How fast was the first pool ball initially moving? That means we are looking for V1 initial. Okay? I wanted to set this up just to show you how to do something a little different. Pause the video, see if you can solve it. If you got the last one, you'll definitely be able to get this one. Did you get a number? Let's see what you got. So, M1 V1I plus M2 V2I equals M1 V1F plus M2. Oh, going too fast, Mr. Norris, slow down. V2F, beautiful. Plug your numbers in. M1, 0.8 times V1I, which is what we're looking for. Okay, put these in parentheses, sorry. VM2, 1.2 times its initial velocity, which is 0 still. Thank you. M1 is still 0.8 times its final velocity, which is 20, plus M2, which is 1.2 times its final velocity, which is 30. Okay, so again, we're just going to do some basic math here. Get that out of the way. 1.2 times 0, aha, 0. That's real nice. 0.8 times 20 is 16. 1.2 times 30 is 36. Trust me on that. So what we have now is 16 plus 36. Okay. And it there. So I'm bringing all this down. So this side of the equation here, all I have left is 0.8 times V1I. And that equals 16 plus 36, which is 52. So do you see how I just did the basic math? I multiplied 0.8 times 20. You get 16. Put it in a calculator, trust me. 1.2 times 30 gives me 36. 16 plus 36 is 52. And now look where we're at. Super easy. You're looking for V1I. This is multiplication. We want to move the 0.8. So we're going to divide, because it's the opposite of multiplying. Divide by 0.8. Divide by 0.8. I actually forget what this is. I think I know what this number is. I'm pretty sure this is, let's see if I'm right. Clear, 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 clear. 52 divided by 0.8, I think is 65. Boom, got it. So that initial ball this time, our initial velocity of our first pool ball is 65 meters per second. Now, I didn't ask any questions about the mass because you have it twice in the equation. It involves a little more advanced algebra, and honestly, we don't see that very often. So it's all about the concept. So the big takeaways here. Number one, momentum is always, always, always conserved. Number two, if two objects hit each other and bounce off, that's called an elastic collision. Think of a rubber ball that's elastic, okay? And number three, the momentum before the collision is always equal to the momentum after. How do you find momentum? You multiply the mass of the object times its velocity. You just add them up. The thing that changes are the velocities. All right? All right, guys, this is step number one in collisions. We're going to keep taking this forward. But you guys are doing great. If you have any questions, email me. Have a beautiful day.